What is 0 to the power 0? The answer to this question is easily found on the internet. So the main purpose of this video is not to just answer this question. Rather, it uses the question as a means for illustrating a number of ideas in mathematics. They are also applicable in other contexts. Before one can answer this question, one needs to know what it means to raise a number to the power of another number. Once we have seen how raising a number to an integer power could be defined, we will deduce what value 0 to the power 0 could possibly be. So we'll begin by looking at the definition of a to the power n, where n is a natural number. Intuitively, we just want this to be a shorthand for writing the product of n copies of a. For example, if we write 2 to the power 3, then we're just looking at the product 2 times 2 times 2. Now we're going to use a different notation. So instead of writing a superscript n, we write POW open bracket a comma n close bracket instead. The reason why we are doing this is to free us from the burden of whatever prior knowledge we had about powers. And so this up here will be written as POW of 2, 3. And our definition of POW a, n is going to be as follows. If n is 1, then POW of a, n is simply a. If n is at least 2, then POW of a, n is equal to POW of a, n minus 1 times a. A definition like this is called a recursive definition or inductive definition. It starts with a simple case called the base case, and then it gives rules for obtaining the remaining cases. Here, the base case is when the power is 1, and for larger powers, they are dependent on the power that is 1 less. And using this definition, we can compute POW of 2, 3 as follows. So the power is bigger than 1. This can be expanded as POW of 2, 2 times 2, and POW 2, 2 can in turn be written as POW 2, 1 times 2, and then times 2. And now POW 2, 1 is just 2, so this is 2 times 2 times 2, as expected. So we now have a rigorous definition of powers, at least for natural numbers. We want to extend this definition to integers, so we want to be able to raise a number to the power of a negative integer. Now before we dive into that definition, let's see what properties of power the current definition enjoy, and see what we must maintain when we extend the definition to negative integers as well. So first of all, from this definition, I can see the following. If I multiply POW a, n and POW a, m, we'll get POW a, n plus m. This actually requires proof, but if you look at POW a, n plus 1, so when m is 1, this definitely is true. And then you can proceed by induction, a proof that is commonly used to prove things like this. The second property is, if you take a to the power of n, and then take that to the power of m, it's the same as taking a to the power of n times m. Again, this can be proved directly from the definition using induction. And the third property is, if you raise the product of a and b to the nth power, it's the same as multiplying a to the power n and b to the power n. Again, you can also prove by induction on n. Alright, so these are the properties that the current definition of power enjoys. What we want to do is, we want to extend the definition of the power to negative integers for n, such that these properties still hold. The reason why we want to do this is we want consistency. We don't want to deal with negative powers as a special case. So ideally, we don't want these properties to hold just for natural numbers, but not for negative integers. Let's motivate this by an example. Consider POW a, 3. Now, 3 can be written as 4 plus minus 1. So I can write this as POWA, comma 4 plus minus 1. Of course, 3 can be written as 5 plus minus 2 as well, but we're just going to focus on this particular thing. Now, if we wish to satisfy this, then what we'll need is that POW of A, comma 4 times POWA, comma minus 1 has to equal to this. Suppose that A is 2, then the left hand side here is simply 8 because it's 2 times 2 times 2. And what about on this side? Well, this over here becomes 16, and this is something that is unknown. But then if you look at this, you'll see that POW 2, comma minus 1 will have to be the inverse of 2. So again, we are using the notation that if you take a number, the inverse of that is a number such that when you multiply it to the original number, you get 1. So if I now replace A with any other non-zero number, I would need that this to be equal to inverse of A for all A that is not 0. A cannot be 0 because inverse of 0 is not defined. Now what about A to the minus 2 as denoted by POWA, comma minus 2? Well, minus 2 can be written as minus 1 plus minus 1. And so to be consistent with property 1, we would need this to be the same as this. So I should say we need. Okay? This is what we need. So what this is the following. So POWA, comma minus 2 needs to be POW of inverse of A, comma 2. And you can continue in this fashion and deduce that POW A, comma minus n, where n is a natural number, needs to be the same as POW of the inverse of A, comma n. Alright, and so this is what we're going to do. We're going to take this as our definition for negative integer powers. For any n, that's a natural number, POW A, comma minus n is this. So this is our definition for negative integer powers. Now, of course, we have to make sure that by defining this, we haven't broken anything. In particular, we should check these two properties for negative powers as well. We're not going to do that here, but if you're interested, you can go try it yourself. Now, notice that this definition for negative powers does not allow A to be 0. And so, this definition needs a qualification for all A that is not 0. So now I've defined POW for all natural numbers and their negations. What about 0? Well, to see what that is, consider the following. Here I'm going to pick A to be just a non-zero number, and this, as we have seen, is just POW of A, comma 1 and POW of A minus 1. And since we expect POW to satisfy property 1 that we have seen previously, we need this. So again, this is need this to be equal to POW of A, comma 1 plus minus 1. And that will give us POW of A, comma 0. So we will define POW of A, comma 0 to be 1, again for all A that is not 0. So this will again form part of the definition of POW. So now I've defined POW on all integers, and we have disallowed the number 0 as our base when the power is 0 or negative. So far I have avoided defining 0 to the power 0, right? Because in my definition of POW, I have avoided that particular case. So the question is, should we give it a value at all? Well, there's really no need to do so just by looking at what we have done. But for the sake of satisfying our curiosity, what could it possibly be? So let's do some thinking here. Suppose it is assigned to some number. Okay, so suppose that it's equal to some number alpha. Then, to be consistent with property 3, property 3 says that if you raise the product of two numbers to a power n, then it's the same as the product of each number raised to a power n. Alright, so in this case, what we need is alpha, which is equal to power of 0, 0, must be equal to POW of 0 times 0, 0. And knowing that we need this property 3 to hold, this will have to be the power of 0, 0 times the power of 0, 0. And both of these are alpha, so this is alpha times alpha. So I must have alpha equals to alpha times alpha. And there are only two possible values. Alpha is 0 or alpha is 1. So if you want to assign a number to 0 to the power 0, it will have to be 0 or 1. Now the question is, are both possible? It turns out that either value is consistent with the properties that we have listed for the powers. For example, to check 3, take any real number a. If we assign 0 to the power 0, then 0 is the same as POW of 0 times a, 0. And this will give us, by property 3, 0, 0 times POW a, 0. And this first value is 0, and this one here, as we saw, is defined to be 1. And so this is 0, which is okay. Now, if instead we define this to be 1, then what's going to happen is this, which is also fine. As you can see here, either definition of 0 to the 0 will not cause any trouble with property 3. And the same is going to be true for all other properties that we have listed. In other words, you can assign either 0 or 1 to 0 to the power 0. But if you read around, you will see that mathematicians tend to define 0 to the power 0 to be 1. And there are reasons for doing that. Mostly it's for convenience of notation. And there are a number of resources on the web that talks about these cases, especially the ones that talk about the binomial coefficient and the empty function. And I encourage you to explore further. What you have seen in this video hardly concludes the discussion.